As it's my first time speaking in one of these seminars, I thought I'd just give a quick introduction. My name is Russell Goyder. I'm not in academia. I work for a company called Zafin. It's a financial technology company. My team applies mathematics to various problems in finance, including pricing derivatives, but also helping banks kind of understand their data better. I come from a place of physics originally. That's my academic background. I'm not a working physicist these days. I've never been an expert in statistical mechanics, but I am very interested in statistical and singular learning theory. I think the connection with StatMech is fascinating, and entropy is a concept that is kind of at the heart of the connection in various ways. And so my goal here is to kind of work on our intuition for the concept of entropy. As you can see in the notes that I posted in the SLT channel, I have just kind of drawn together a few of my favorite sources on the topic. And I'm hoping to give a bit of a guided tour, and I hope it's useful, and maybe I don't know, some sort of light relief or entertainment or complementary somehow to the kind of main thread, if you like, of this seminar, which is more mathematical. So, the overall structure, so let me try and write on the board, here we go. Physical, there we go, and information in formation entropy. The overall game plan here is to kind of do this one first. Look at entropy from an information theoretic point of view, and then do this one, and then already by the time we get to sort of the latter stages of number 2 here, connections between the two will be clear and emerging, but I think we can kind of focus further on those connections. Look at how intimately they are related. I mean, they're really, without wanting to, give you any spoilers. Well, those words aren't really well chosen. Here's a huge spoiler. I think they aren't really different things. They are the same thing, and I think that will come through quite strongly as we look at the topic. Okay, so let's start with not entropy, but information. Right, so I have n outcomes of some, in quotes, random experiment or some process. I have some probabilities. The probability of the ith outcome is pi. Right, so I guess that is true, where I is an integer, positive integer. And I want to say that the information associated with observing the ith outcome that occurs with probability pi is the logarithm of 1 over pi. And I'm giving you a plausible definition of the information associated with that outcome. It's not kind of rigorously, it doesn't come from anywhere deeper than us just wanting an additive measure for compound events, right? So if I have, if my experiment is actually, n has n times m outcomes with probability pi and qj, and these events are independent, then the probability of the ijth outcome is the product of pi and qj. And if I have a logarithm in my definition of information, then the extra information I learn by discovering the qj part of that product is added to the information I've got from the pi part. So that's what the logarithm does for us. And this part, the reciprocal here ensures that that surprises are teachable moments, as it were, right? So there's more information when we're surprised. If what we see happening is what always happens, then we haven't learned as much as if what happens is an unusual event. So rare outcomes convey more information. And so I just like to, this was covered implicitly in an earlier seminar given by Dan, on Shannon's source coding theorem, with a nice follow-up on the Kraft-McMillan theorem. But I listened to both, and I still found that I benefited from kind of going through a couple of examples to understand the sense in which this definition of information makes sense. So I'd like to just quickly take you through those examples right now. Maybe a brief pause for any questions or comments so far. You're all still there? We're okay?
Yeah.
Okay.
Yep. Maybe it's a bit ahead of time, but I guess what you've motivated is to have some increasing function of 1 over pi there, but it need not be the identity. Is there any good physical reason to want 1 over pi as opposed to, I don't know, some other function of that?
Yes. And we'll get there soon. Those reasons. I mean, so I think the ultimate formula that we know and love for information entropy of a distribution is uniquely determined by Shannon's 3 axioms. So I think the answer lies in those 3 axioms. So the first example, to kind of build our intuition muscles for this idea of information, is similar to 20 questions. It is the game of 16. Okay, so I'm thinking of an integer n that is from 0 to 15. And you need to guess what I'm thinking of based on asking the questions, right? And the questions that you should ask are as follows. The first is n greater than or equal to 8? Is with an S. And I'm going to just play it through with a couple of values here. We'll do 13 and 6. Right, so that's a yes, and that's a no. In fact, no, yeah, that's fine. We'll keep going like this. Okay, and then is n mod 8. Is that an acceptable notation among you people for
Mod 8.
the modulus?
Yeah, I've never seen that before. That's interesting.
Okay, good.
Yeah.
So in that case, I'm going to get rid of it. And I'm going to use
the programmers among us.
is n mod 8 greater than or equal to 4? Is n mod 4 greater than or equal to 2? And is n mod 2 greater than 0? Right, so the remainder after dividing 8 into 13 is 5, and that is greater than 4, so that's a yes. N mod 4 is 1, which is less than 2, and so that's a no. And then n mod 2 is 1, so that's a yes. And just for speed, from my notes, I have no, yes, yes, no. Right, so these are, like in each question, we are revealing one of the bits in the binary representation of these numbers. Right, so 13 is 1101. 6 is 0110. And like if each integer choice that I make in this game is equally probable, then the outcome of each question has the same probability, pi of 1/2. And so hi is log 2, which, if my logarithm base is 2, is an amount of information of 1 bit. Right, so I haven't put a 2 here yet, and I don't need to, of course. Right, that's just units. If it's an E, I've heard the unit called the NAT, N-A-T, for natural logarithm-based information unit, or whatever, I guess. And you know, the Kraft-Macmillan theorem says that you know that if your alphabet is short, then you need longer words. But if you have a very long alphabet, then you can get away with shorter words to encode the same information. We could use logarithm to the base 10 here, and then I suppose the unit of information would be the digit. We could use 26 as the base of the logarithm, in which case the unit might be the letter or the, I don't know, Roman, Latin alphabet letter. and so on and so forth. But I think bits is a pretty good choice here, so I'm going to put a 2. Okay, so that's the game of 16. That's a kind of starter, and I again will maybe I won't leave the board, but I'll pause for any questions or thoughts before moving on to a more like a less trivial case, where the PIs aren't all the same, which I think is a bit more instructive. But this is perhaps a good warm-up. Okay, so I'm going to hit the red X, leave that board, and have a new board. Great. Actually, would you mind, Dan, putting the first image up here?
Yeah, sure.
So this is the game of Submarine. And it's very similar to the game of Battleships. Can I take a quick poll among you? Who knows this game, Battleships? It's a board game.
Yep.
Okay. Okay, good. All right, so this is a simplified version of Battleships, where a submarine, which is 1 square in size, is hiding somewhere in the board. And it's one-sided again. So you just keep guessing squares, and I tell you, one by one, whether you've got a hit or a miss. And that's a miss. That's an X, and then the check here is a hit. Okay, so we actually know that the submarine is in that square. Okay, so there are 16 squares, and so the probability of a miss, that's the X, on the first guess is 15/16. And the information revealed by a miss on the first guess is, log 2, 1 over that, so 16 over 15, which is about, 0.9 bits. Right? It's about 1/10 of a bit that you learn from that information. From that outcome. In contrast, if on the first turn you're lucky enough to get a hit, well, that occurs with probability 1/16. And the information derived from that outcome is, 1 over 1 over 16 is 16, is 4 bits, which makes sense because the location of this submarine is, can be represented, parameterized, I suppose, by a number, right, from our previous game, 0 to 15. And we know that, we can represent such a number with 4 bits. So I think that makes sense. Now on the second turn, we can keep going. If we didn't get a hit on the first turn, we've got the probability of a miss on the second turn being 14/15 now, because we've eliminated one of the one of the squares, that one on the first try. And let's suppose that we guess here. We get a little more information now. hx2 turns out to be, well, it's log to the base 2 of 15 over 14, which is another approximately 1/10 of a bit. It turns out to be 995 something something or other. Now, if we're lucky enough to get a hit on the second turn, then the information we learn from that is log 2 15 over 1, which is about 3.91 bits. And if you add that to that, you get exactly 4 bits. Again, because you've discovered the location of the screen, you've learned a number between 0 and 15. So, would you mind down the next board, the next image on the next board? We're just going to kind of cut to the chase and jump to the 8th turn and consider another few special turns. I see it. Thank you. Huh. I'm sorry, I think I'm going to have to go out, leave and come back. Oh, no, I have it. Great. I don't know how, but I tapped this right, I guess. Okay. So what we know at this state of the board, right? I've got 1, 2, 3, 4, 5, 6, 7, 8 x's. We know that the submarine is not in half of the squares, and if you compute this sum, you get 1 bit, it turns out, which again makes sense, right? It's like the first of the 4 questions in the game of 16. And by the so this is the 8th turn, the 9, 10, 11, 12th turn, you get 2 bits, because we've only got a quarter of the squares left, and I think actually the 14th turn gives you 3 bits of information, so we'll just add those in green, like here and here, 12, 13, 14. And so there's one bit left to learn in these remaining squares. Right, so there are some special turns. Sorry, let me just put that up here. It's not going to take too long. By the 15th turn, we've accumulated all 4 bits of information, right? Because, so there's the 15th turn. Even if it's a miss, we know where the submarine must be. Okay, I'll make some space for myself here. Okay, so there are, you can see that the total accumulated information from misses is some real number according to the base of the logarithm, and well, it's 2 here, and so the logarithm of 13 twelfths or whatever is not a particularly round number, but there are special turns where we have eliminated half the squares, 3/4 of the squares, and so on, where the total accumulated information is these nice round numbers. But of course, we know that when you find the submarine, you have learned 4 bits worth of information. And it doesn't matter what turn that happens on. I can accumulate the information from n minus 1 misses, and then add a hit on the nth turn. Right, so that gives me the sum over logs, which is the log of a product of 1 over pi multiplied by the final, sum of, I'm adding the log of the hit, 1 over the hit probability, and so that can go into the product as well and be 1 over p n. I'm sorry. That's not quite right. Let me... So these are probability of miss on the ith and the probability of hit on the nth, which is, well, in this case, we can start writing these down, right? 1 over px1 we saw was 16/15, and then we had 15/14, and so on. And then ultimately we get to 1 over n, which is n over 1. And the previous term is n plus 1 over n. Right, so there is much cancellation here, and we end up with just the start and the end, which of course is 4 bits. Right, so that works out and matches our intuition, which is that by the time we've learned where the submarine is, we've just nailed this number from the first game, the coordinate, if you like, of the submarine, which is a number from 0 to 15. So that's it.
It's a really
that's
satisfying example.
My intuitive. Sorry?
I was just saying that's a really satisfying example, the cancellations.
Yes. Yeah. Yep. So that's my kind of intuitive feel for why that definition of information makes sense. And now, we're ready to kind of use it. Maybe I'll do it on the same board, given also the board risk. Right? We're ready to. Oh no, I won't. It's worth a new board. So here we go. Sorry. Huh. There we go. Sorry, I'm experiencing operator challenges on the iPad. I occasionally drag. I forget that when I touch a board, it goes into edit mode. Sometimes I want that screen real estate for changing the direction of view and so on.
Yeah.
So, now we have entropy as average information content in a distribution. All right, so I was just saying that, I think the minus sign here and the log are doing most of the heavy. I mean, you know, this to me is really, there's nothing, you know, the only new thing here is this, right? We already understand everything to do with little hi, and the minus sign and the log are really all that's kind of going on there. And we've just added one new ingredient, and so that's kind of it. That's what, you know, entropy makes sense to me as intuitively as the expected or average information content available in a given random variable's probability distribution. Okay. So then, I still haven't, you know, there's nothing particularly rigorous here. We've just sort of motivated the three things in the blue rings. But what Shannon did in his 1948 paper, it's listed on the first page of the notes, it's one of my sources, is he showed that if you assume that there is a measure of information that is continuous, that is monotonically increasing as a function of the number of possibilities, number of possible outcomes, and self-consistent in a certain sense, which we'll get to in a second, then there is only one functional form that satisfies those given a probability distribution, pi. And really, it's this one where almost all the action is. His proof is discrete, and he uses the continuity property to kind of extrapolate between rational numbers to real numbers. And it's a kind of afterthought. And the monotonic increasing property is used. It is used. I don't want to undersell it. But the main, the main action is in this self-consistency. And what I thought I might do, I don't know, maybe I should get your feedback here. I thought I might, I can either kind of go through the whole proof, or I can give you a bit of a primer that should be useful if you go and look at his original paper, which, by the way, is really clear. I mean, sometimes when you read historical papers, like Einstein's papers are in a different sort of notation, different language from today's expression of them. But Shannon's, it spoke very clearly to me as a reader 80 years on. So let me start with the guided tour, like the sort of the primer part, and if that's enough, then maybe we can move on. But if there's an appetite to kind of go deeper, maybe we can choose to do that at that point. Okay. So what Shannon, the example that he has in his paper, which is the same example that Jaynes uses, by the way, when he goes through this in his book, Probability Theory, the Logic of Science, is this. He says that that let's say you have three possibilities, three outcomes, with probability 1/2, 1/3, and 1/6. Sorry, I'm just looking at this. Yep, okay, good, sorry. And it looked wrong for a moment, but it's not. Versus the same information ultimately being revealed, but in stages. Right, so first we have equally likely outcomes, and then so that's 1/2 and 1/2, and then a 2/3, 1/3 subsequent I don't know, choice event, random experiment. Right, so 1/2 of 2/3 is 1/3, and 1/2 of 1/3 is 1/6. Right, so we get to the same probabilities ultimately, but they're revealed in two stages. Self-consistency to Shannon means that whatever the functional form of HP is, as a function of the first set of probabilities, the first distribution here, that should be the same as, well, the information gained from the first stage plus well, a half, because it happens half the time, and then the information gained from the second experiment, if you like. And he has some notation for, well, used throughout, which is particularly relevant here in the monotonically increasing axiom, assumption. And that is that if all of the outcomes, the n outcomes, are equally likely, then pi is 1/n for all I. And we're going to define an A of n, which is the information revealed in that case. Right, so it's A of n that is monotonically increasing. Okay. Next board, which we can't look at the next set of boards, right? Okay, that's fine.
Yeah, we can't. That pair isn't a thing. You said how many pages the paper is? How long is the proof, roughly? The setup is on one page, and the actual proof is in an appendix, which is another. It's short. It's like one page. Yeah, I have not read the proof of this theorem, so I'm quite interested to hear.
Okay. I think in my notes, for me, it took a little while to kind of get my head around what he meant by the self-consistency property. So I'm just going to draw. I don't know. I feel like slightly indecisive about whether this is worth your time or not. But I think I should probably just chill out and draw it.
Yeah, you can never go wrong with a picture.
Okay, so I just wanted to draw a more complicated, non-trivial example of the kind of thing that he might have had in mind, with some probabilities here. R1, R2, R3. This will be S1, S2, S3. T1, T2, U1, U2. Okay, so here he's saying that H of, well, the first root is P1, Q1, and the second root is P1, Q2, and the third root is P2, R1, S1, and so on, all the way to the last root, which is P2, R3, U2, must be equal to, well, the first stage is H1 of P1, P2, plus, well, with probability P1, we've got H, this is H, I'm dropping the P, but anyway, that's maybe okay. H of Q1, Q2, up top there, and then P2, with probability P2, well, now we've got the same thing nested, right? So H of R1, R2, R3, plus with probability R1, H of all the S's. Let me just, as a shorthand, draw right vector S, and R2, H vector T, R3, H vector U. Okay, so that's what he means by self-consistent, right? I think that's the sort of thing he had in mind. And the proof, and so if you are able to look at the previous board and see that the quantity A n defined, right, which was H of 1 over n dot 1 over n times, my n's need a bit more discipline there. Well, he shows, well, that, well, actually he doesn't show, he just uses the fact that A of S to the M is M times A to the S. And I think it's probably worth a quick picture for that as well, which is this one. Right, so this is M. It's not. M equals 1, M equals 2, M equals 3. This is 2 to the 3 equals 8, right? So M is, this is stage 1 and stage 2 and stage 3. And the total number of stages is m, which is 3, right? So s is 2, m is 3, and of course s to the m is 8 in this example. So if we take the direct route, right, and go straight there, like that, then we have h of 1 over 8 dot 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 1 over 8 with commas maybe, right? So that's a to the, sorry, a of s to the m in this example. And if we apply the same scheme as the above, we get, well, let's use the a's. It's a of 2 for the first choice. And then with probability half, we have the second stage, right, which gives us an a of 2. But within that, so, you know, just as we had inside this square bracket here, we have the third stage, and we have another copy of this. So I'm going to do a little more color coding in a second. So these come from here, and that these and these come from here, 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 and here. And if you add all that up, it ends up being 3 a of 2, which in this example is m a of s, which is what we were trying to, well, which is what is what we were trying to show. And we, you know, it's only one example, but I think you can see how it generalizes to any s and any m. All right, so I will go to the next board. We're already looking at them both OrbCam wise, right? Yes. Good. Here I am. So just to recap then, right? Where are we? We've got Shannon's axioms, 1, 2, and 3, continuity, monotonically increasing, and self-consistent. And the self-consistency is where we've been sort of focusing. And that, something quite key there is this property of A to the S, A of S to the M, equaling M, A, S. Oh, lordy, sorry. I can do better. Okay. So then, what he says is consider a total of n outcomes, but organized into little n groups, right, with little ni outcomes in each group, right, with the probability that you hit the ith group being that. So we can apply the self-consistency property to that, right? We can say that that a big N, right? So that's going all the way to the large number of kind of micro outcomes, if you like, can be written as h of p1, p2, to pn. In other words, like this is the thing we want. This is HP. We want to discover that functional form. Plus, well, now we sum over with probability pi the same functional form applied at the next stage or the next level. Now, there's something that he needs and shows separately, which I do have a page in my notes on, page 7a, but I'm just going to state it for now and get to the punchline, and then we can decide whether to kind of go through that part or move on. Right. So what he states is, well, he shows that the functional form of A applied to some integer must be some constant times the logarithm of that integer. So that's a little bit magical at this point. I'm just sort of introducing it. The increasingness of the functional form just means that this constant must be positive. That's the only place that the second axiom, or the fact that it's an increasing function, is used. But the monotonicity is used in order to show that A must have a logarithmic form. But if it does, then we can apply it to this. We can say that we must have C log big N, in other words, the sum over the Ni on the left. That must be equal to the thing we want plus, well, C sum over I, Pi log Ni. And so HP must be equal to, well, knowing the answer, let's pull the minus sign up front. And we have, sorry, delete. What's happening? Oh, that's right. Okay. So this this isn't a function. This isn't once you've summed over the i's, right? There's no I dependence there, right? So so that's a plus C. So I have this, right? So I can insert 1 in the form of that in here. And I have log of that same thing. In fact, I don't really know why I didn't just call this n first time round, so I'll do that now. And by the time I, combine these in this way, so this, of course, is pi. And because this c is positive, I can absorb it into the logarithm with a suitable choice of base, and therefore unit. Okay, so we started from Shannon's axioms. We understood, with some examples, what the third one was talking about. And based on what's in the box in the middle here, this one, we have the answer. So the only missing piece is where that comes from.
I'm dying to know. What were the other things? How long will that take to explain?
It's one board if I arrange the writing artfully.
Yeah, I guess I would vote for going through that. I guess that means maybe you will defer some other things until the second part of this. Do you mind doing that?
Okay.
Or, I mean, it's up to you.
I don't mind at all. No,
Yeah.
let's do it.
Cool.
All right. So here we go. Okay, the boards seem to be playing ball, which is nice. Okay. So we've got A of k is C log k. Right, so that was in the magic box. So what Shannon says, I believe, is that for I think for rational S and T, given T to the N, I can find an M that sandwiches T to the N for any other S.
I guess you want these both to be positive rational numbers, right?
I do. So that's his starting point. And he takes logs of both sides, right? So M log S is less than or equal to N log T, which is less than or equal to N plus 1 log S. I think he would divide by n log s to give the m over n is less than or equal to log t over log s, which is less than or equal to, well, m plus 1 over n. And he says that he's going to do this for an arbitrarily large n and call 1 over n epsilon. So that means the difference, the absolute difference even, between m over n and log t over log s is less than or equal to epsilon. So then he goes back to the beginning and applies the information measure to these values. So a of s to the m. And because it's monotonic, these inequalities are preserved. And because we know that a of s to the m is m a to the s through the third axiom, the self-consistency property, we can write that as m a to the s is less than or equal to n a to the a of t and then similarly we can divide by n a of s. Cancel. Epsilon. Cancel. Cancel. So just for a better visual, let me just write this then. We have something that basically looks the same as we had before. And so from that, the absolute value of m minus n, m over n minus a of t a of s is less than or equal to epsilon. All right, so I mean, if this is m over n, say, and that is log t over log s, and that's our epsilon, then the worst case, I suppose, is that a of t over a of s is over here, and that's another epsilon. So I can subtract these two to give the absolute value of a of t over a of s minus log of t over log of s is less than or equal to 2 epsilon. But I mean, the 2 is no big deal because I can run this whole thing for an arbitrarily large n and therefore an arbitrarily small epsilon.
I just
So in
check.
that limit,
the original statement is that for any n, maybe say capital N, for any capital N there exists a pair little m comma little n with little n greater than or equal to capital N and little m and n satisfying that inequality, right? Like you somehow need to be able to make little n big and have m work alongside that little n. Is that right? I mean, it's certainly not true that
This,
that will work. Yeah. So we
you're
just
focusing on that, right?
that's right. Yeah.
Yeah, I mean, if S and T are the same, then
And it's certainly not true if I take S and T arbitrary that there always exists a pair little m and little n, right? If
yeah, that satisfies the red box.
I think that's well. I guess you need to worry about things like t equals 1. In our case, S and T are both less than 1, right? We don't.
No.
No. Oh, sorry.
Yeah.
S is.
In my example,
Yeah. Okay.
S was 2. I think S and T are quite large.
Yeah, that's right. Okay, so they're greater than
Because
1.
they're the one over. They're the number of possible outcomes in the distribution. So maybe if T is 10, say, and S these are all quite large. Yeah, it's a good. You're right to question it, and I, to be honest, don't fully. I haven't thought through what's in the red box. It was just sort of stated as a starting point, as far as I can tell. But maybe there's something else in the paper that gives more background. So maybe that's a bit of homework for next time. I can have a look.
I guess you need the. Yeah, all right. I mean, I think all you need is that you can find a pair little m comma little n with n larger than a given integer, and then the argument works, and that I believe. So yeah, I think it's fine. It's clever, obviously, to think of doing this.
Yeah. Yes, indeed. Yeah. So I get lost in the 4 degrees of freedom. The S and the T and the M and the N. I mean, I can well believe that if there's an S and a T and an M and an N such that the first inequality holds, then by multiplying another S, I make the left-hand side now bigger than the right-hand side of the ST inequality on the left there. But anyway, let me perhaps dig into that ready for next time.
So I guess
So to complete the flow.
Yeah,
sorry.
No, I was just going to say. So it seems like we're basically done now.
I think so. Yeah. I mean, basically, this is let's call that 0. We're among friends, and n can be as big as we like. And so, yeah, if and so that's an equal sign there.
Even among enemies, the left-hand side is independent of the n or the epsilon. So since it's less than or equal to any given arbitrarily small real number, it must be 0. So yeah.
Right, and yeah. So given that, okay, so if it is 0, then I can write this down, I suppose. Well, in fact, yeah. if that is true, given that, I've got an arbitrary function of t on the left and an arbitrary function of something else on the right, of s on the right, then they must both equal a constant, or at least something that doesn't depend on s or t, and those are the only variables. So I think we've got our box now.
Yeah, that last bit I'm a bit curious about. So it's definitely true that at on log t. Oh, I see. No, that literally says that it's a constant function because it's for arbitrary s and t. Sure. Yeah. Uh-huh.
Yeah. I remember first meeting that argument when separating variables in partial differential equations, for example.
So this part doesn't use the self-consistency at all, right? So this is just, well, we haven't used continuity yet. I guess you're about to do that, as you said, to get from rational to real.
We have used the self-consistency here.
Oh, of course, yes.
Yeah, and I don't know what to say about going from rational to real, other than in fact, I don't fully understand it, to be honest. I mean, there's just like a throwaway sentence at the end.
Yeah, this part I can explain. So you've shown that you've assumed the existence of the function a, is that right? So if a is a continuous function, and on all rational numbers it agrees with the continuous function c log, then two continuous functions which agree on a dense subset must be equal. So the rationals are dense in the reals, so that is, you're done.
Right. Okay, awesome.
That was so clever. I'm so glad you presented this. I hadn't seen this before. That's very nice.
Yeah, and I'm looking at the time, and I think, as I look at my notes, the next board would be the physical entropy part of the story. So we have spent longer than I thought, but maybe it was worthwhile. And so maybe next time we can do physical entropy and see how far we get in the connections between the two.
Yeah, sounds great. Any questions about this part for Russell? Seems not so far. Yeah. Yeah, what was next in the notes? Sorry, I didn't quite follow what you said. I was thinking.
No problem.
Yeah, what would you like to do in the 5 to 10 minutes we sort of have left? You want to... I suppose it's not obvious at all from what you've said so far that this has any relevance whatsoever to physics, right? Why...
Yeah.
What is the secret to why that will be the case?
Well, maybe the best thing to do with the last 5 minutes is sort of tantalize and hint in that direction. Because I think to fully explain, no, maybe I can do more than that, because tantalizing and hinting would just be a non-obvious. But I can't do it all. So let's see what I can do. So that we're now on physical entropy. Right? So there's something else. There's something which is people call entropy, which has very different roots, and this is it. I mean, I'm just going to write down a formula that says inverse temperature is the rate of change of something called physical entropy, S, with energy. And we're going to, the easiest physical system to consider here is a gas. So let's say that it's at constant volume and constant particle number. Number of particles and volume. And this is the internal energy, which just means like this gas might just ignore external fields, essentially. Right? The fact that the gas might be on a planet experiencing gravity, or subject to some external, I don't know, electric field, say, which starts sort of interfering with the charged particles in the molecules of the gas. All that sort of stuff, ignore, and just consider the energy in this gas that it would have in a complete vacuum with no other sort of physical influences coming from the outside. All right, so there's a story, like a thermodynamic story, to do with, Carnot engines and Clausius. And it was Clausius, really, who established the existence of something called entropy. He even chose the name. And this was before the existence of atoms was discovered, right? This was based on very kind of general arguments to do with trying to make steam engines better, essentially. And so it's really not a priori obvious at all that that S is the same thing as our H. But the clue is in the subscript, or the lack of subscript. Right, so everything on the left over here is to do with kind of macroscopic measurable properties of the gas in your piston, without knowledge of any kind of microstructure or microstates. It's when you look at this picture on the left in terms of the statistical properties of the microscopic description of the system, that the two ideas are reconciled. So that's the journey that we're on.
Yeah, I find it astonishing that physicists can find some coherent theory in a state of such confusion and lack of foundations. Thermodynamics is an amazing example of that. I would have just given up if I were in their position. It's just so difficult to see through the mess of stuff they had in front of them and come up with a concept like entropy. It's really amazing. I just looked up the etymology of the word. I don't know if it was used colloquially before Clausius. Maybe not. I mean, now, of course, we use it in everyday language, or at least I do.
Yeah.
But it says that it has its roots in the Greek entropia, which means a turning toward or transformation. That's very appropriate.
So I do know that it wasn't used before Clausius. He felt that it was such an important concept that it deserved to have the same name in all languages. And so he invented what he felt was an appropriate term. And part of his motivation for the final form of the word was its similarity to the word energy. So his PhD thesis, I think, essentially was the statement that the energy of the universe is a constant, but the entropy of the universe isn't, and increases.
Yeah, I guess these days many people would argue that entropy is a more fundamental concept even than energy. So Clausius certainly was right in spending the effort to come up with a good name.
Yeah, yeah, indeed.
Thanks a lot.
And I know what you mean about the challenge. I mean, there was this concept of caloric, which turned out to be nonsense, but it was not a bad guess at the time, kind of thing.
Yeah. Yeah, I think it's easy sometimes for mathematicians to underestimate what part of physics is actually hard, because they often encounter the thoroughly digested, simplified, cleaned up version 100 years later, and they think, well, how could this possibly have been difficult? Look, even I could have thought of this. Physics must be so trivial. Of course, all the information and effort is somehow in that process of to come up with these ideas in the context they were discovered is really, really much more difficult.
Right.
I don't know if you can hear the cow behind me. It's dinner time here. Any questions for Russell? I guess we're going to pick this up either on the seminar will take a break now. This is the last one of this year. We'll start again on the 19th of January. I'll speak over the cow. So I don't know, Russell, if you want to give the first talk of 2023 or one of the... hopefully it's like this first or second. Are you willing to start off next year on the 19th?
Yeah, I'd be happy to. I can carry on. Yep.
Great, terrific.